YouTube. I'm here in my home-based studio from where I will give a talk today at the third Brain-Computer Interface conference. This conference is organized by my colleague Professor Moritz Grosse-Wentrup, based at University of Vienna. My talk will be about continuous movement decoding from non-invasive EEG. See you there. So my talk is, as we said, about continuous movement decoding from non-invasive EEG. And you all know more or less that this is one of our main focus in research to really derive a brain signal in a way to capture movement and the intention to movement, so that a person with a high spinal cord injury can either control a neuroprosthesis or robotic arm to get arm function or hand function back, and so improving his or her quality of life. We work on this topic now for a bit more than 20 years. I want to present you a bit what we did in the last couple of years, mainly dealing with the project MoreGrasp and the Filia-Rich project. So what we were looking for is a natural control of grasping and looked for a new signal, or for a different type of signal, moving away from motor imagery. And here we use a movement-related cortical potential, and we were curious whether it's possible to differentiate different single limb movements like opening the hand, closing the hand, pronation, supination, and so on, or even differentiate between different grasps like the pincer grasp, lateral grasp, and key grasp. So grasps which are necessary in daily living. And what we find is that we can measure these MRCPs related to that movement. We can also differentiate them to a certain extent. We transferred this knowledge to a series of spinal cord injured patients to find out whether we can also transfer what we have learned from the studies with non-disabled, whether this is also transferable to people with spinal cord injury. What we see is we can still measure MRCPs when people attempt their movement like pronation, supination, different grasps, and open the hand. What we also see is that really the neural pattern is originating from the motor area. So these were some works by Patrick Ofner and Andreas Schwarz I have presented so far. In the MoreGrasp project, we also wanted to, or we included a lot the end users, so people with spinal cord injury. And as we see here, in another end user where he was attempting a movement and could grasp his toothbrush. Well, by the way, we were using here a water-based electrode system, which was also developed in the project. What we also could find, and this is again work by Patrick Ofner, is it possible to detect this MRCP, which is really a tiny signal, asynchronously. In a proof of concept study, Patrick could show that by a specific training program which really rules out any external cues and disturbances to the EEG data, MRCPs could first be elicited, induced, and a classifier trained, the panel on the left side, and then in an asynchronous online scenario, he could detect that an MRCP occurred, and then also differentiate in the shape of the MRCP whether it was a hand opening or a hand closing. Of course, this was really fantastic to find out in a spinal cord injured person. What we also see is that we still have a high rate of false positives, and this is of course still something we are working on. This so far is fine, so we could identify new pattern which we will work on. We can detect different hand movements, different grasps, and so on. But still there is nothing talked about yet about the whole arm movement. And sure, this is something we would like to do. We would like to to have the full arm control with a non-invasive EEG. And the idea of the following grant, of this failure reach grant, was whether is it possible to establish the knowledge to really decode movements of an arm and more. So what we put into this project was when we start a movement, then of course we started at some point, and there we want to find out, we only want to decode trajectories when the movement has a goal. So this was one of the first projects. Then movement decoding has to go on to really find out from the EEG signals whether to, for example, move a robotic arm. Still, we know that the decoder will not be perfect, so we included the detection of errors, but not in a discrete way. So we were looking for, is it possible to detect errors from a continuous way. Also, we studied how does signals change when we give feedback to a user, so to improve the patterns, when the person can also, for example, feel the movement of a robotic arm while he or she can observe it also, so that the patterns get more stable. And then the final thing would be to detect a correct grasp, what we have seen already. First, I want to show you the movement onset detection. This was the main part of the PhD by Joana Pereira. And there we did a task where the participants either looked to a specific target, or they looked and moved their hand and grasped to a specific target. We analyzed the data, and when we trigger on saccade onset, we see in the upper right panel that we have some activity in the motor and parietal areas just before the movement onset. When we analyze the data, and it's the middle panel, only in the look condition, we see lesser motor activity, and when we do the contrast, we see that the motor areas is nicely to differentiate with. This study also contains asynchronous detection of these movements. The paper came out just recently. The other thing was to detect errors. Is it possible to detect errors when there is when the decoder, for example, would make a mistake and the robotic arm would move somewhere? And so we did several studies. This was the work of Catarina Lopez-Diaz, where we studied masked errors, errors during continuous movement, and so on. And we could show that even if it's not so clear when the exact error happens, still our error processing system works, and even we can detect, even asynchronously, the error in the setup. So a small movie here, or video here. So we see that the person here is moving with the hand, and the robot is following to a target. In this trial it was correct. In the other trial, the robot does a mistake movement, which the subject does not know, of course. But the system she is wearing is an online error detector, and there can be an undo function done automatically, and she can perform the final movement of that robotic arm. These studies were done with people, with students, non-disabled people, but also with people with spinal cord injury. And now let's go to the decoding of things. So we did many studies. They are mentioned here, mainly on the left bottom here, by Reinmar Kobler, where we looked into how can we decode 2D movements from EEG, is a direction decoder possible, and so on and so forth. Finally, we could conclude to put this all together to an online study here by Valeria Mondini and Reinmar Kobler together in JNE, where we first let the people move on a surface. They were following a snake and a robotic arm on a screen. The robotic arm was real. The kinematics was recorded with the EEG data, and the kinematics and model was calculated, which we then were used for online feedback. First with a bit of EEG, then with more of EEG, and then with 100% of EEG, as we see the numbers 33, 66 and 100. And so slowly let the people go into the more into the situation where only EEG is really used for the decoding here. What we see here, correlations with the kinematics were around 0.3, so this is clearly above chance, which was around 0.1. What we see in the lower panel here is that the decoding result is kind of in phase with the real movement. We see X and Y position here. What we see is a clear mismatch of the amplitudes. And we were struggling a bit with this because the less the contents of the kinematics was, the larger the movements were so that the decoding works. So what we finally did, we included not only position and velocity, but also the speed from the velocity. So to match for the amplitude. Again, we performed a study. Here, this was the work by Victor Martinez Cagigal and the whole team of the Filia Reach people. The basics were also presented by Reinmar here again on the right side. And we were performing a very similar study, again online, which I don't want to show you numbers, but a small video. So here we see, hopefully, the person is moving still the hand, trying to follow with the robot the snake on the screen, but the movement of the robot is purely organized by the EEG signals you see from the recording we do. And we see to some extent this works, but this is far away from perfect, of course. But this is pure 100% EEG. So what we did next is when we want to transfer to spinal cord injured, we said let's do it very similar to people did in the early 2000s and before. We strapped the arm of the participant like they did with the monkey studies and do the very same. So people could attempt the movement, of course activate the muscles, but not really perform the movements. In a single case study, a first try, we see that the correlations in X and Y and as a position and velocity go down, even does not work in a pure control. What we also tried is, what happens if the user is allowed to freely control? And we found out that, or we tried that the person could freely, for example, follow a diagonal on the screen, to the left or to the right, or even to make just circles. And here we see the principal components kind of indicate that this could work, but not really. And we said, let's let the users train here. What's user training? And this brings us to the next online study, which it was performed by Hanna Pulverer, currently submitted to a journal. She trained 10 participants. Every participant had to do 3 sessions within 5 days. The setup was very similar. We removed the robot. And what we find is here that there is a kind of a general training effect visible. We see this in some areas of the sources where you see the specific regions of interest here in these color bars on the right side. We see the activities from one session to another session in terms of position and velocity. And we see also a free moving result exemplarily for the diagonal 1, 2 and for the circle. So we could see that training kind of worked at least from step 1 to 2, but in the third, the expectation, what we assume is could not be reached anymore because this is a 4 hours experiment. Yeah, people were not so motivated in the third session. This is one of the things we assume here. Anyway, we also went, or at least we invited a spinal cord injured end user into our lab the person has received a spinal cord injury with a level C2, so very high here in the neck. He is a complete spinal cord injury, and what he did in the first setup, he just observed with his eyes the snake on the screen. And we of course always remove the EEG from the EEG data. I did not mention that extra, but it's written in many details in all the papers we write. And from the decoding we can do, because in the processing of the vision, we could even infer the trajectories in some sense. In the next session we invited him again, this was a couple of weeks later, and then we asked him also not only to observe but also to attempt. You see the patterns for position and velocity there and the difference. So they are different, we are not so clear with the results yet. It seems it contributes that he not only observes but also attempts, motor areas are involved. And this brings me to my last slide and to many open questions, of course. First big question, what's about the real world? So, can we use MRCPs for grasping, for cylindrical movement detection? This is what we still need to investigate. Yes, it works in a kind of, but not in a way that we can apply it to a patient at home so that he or she can use a neuroprosthesis. This is honest and the truth, and we are working on this to improve that. A big question, maybe I should not have put this in the middle here, but more on the end. Will end users accept the BCI system in daily life? I think a question for many of us here in that audience. Would such systems be beneficial? We often make the experience that the people use it because they want to help us, they want to help science, but in the end there are too many cables and it's a mess finally. So we need to improve here, everyone in this room. The whole arm controlled by a BCI, this is what I showed you in the second part here. It generally works, but for a specific task, moving the hand somewhere. We are working on this, we are not there yet. Does it work in end users with high spinal cord injury? We see indications that it could work, so we are having high ambitions here. But what we see is we have a lot of calibration. We need to calibrate the eye correction, the error processing, and so on and so forth. And this is something where our experiments at the moment are about 3-4 hours, 5 hours, and this is way too long because we calibrate for 2 hours before we can do the experiment. And this needs solutions for the future. Of course, we have things in our mind, but that's it. And this was my talk today. I acknowledge especially my lab, the Field Reach team. Of course, I want to acknowledge about 320 participants in the studies in Field Reach, 10 with a high spinal cord injury. Thank you very much for your attention. I hope you enjoyed my talk, and if you have questions, please put them down into the comments, and I will give you a list of papers down in the explanations of this video so that you can look up all these papers very easily. I'm happy if you would follow my channel, and I'm looking forward to see you in my next video. Bye bye.